All right. Right, I hope that I'm audible. All right, okay. Are you guys okay? Good evening. All right, I'm so glad to be with you in the evening. Firstly, I want to apologize. Good evening to all of you that are joining me even online. Firstly, I just want to make sure that I apologize. We're meant to start this live at 7. However, life being life, things happen. I hope that you don't even mind how I look right now. And thank you for joining me. Right. Hopefully, we are going to have more people join us online. So, welcome to our evening session. We are going to be looking at some sizzling questions on chemistry. So, today I am going to be looking at the 2025 May-June exam that was written recently. And what I did is that even though some of you had sent me questions, but I thought I will address the same sections on the same body of work on the 2025 exam with the hope that I will be able to inadvertently be able to answer those questions. So this is the question paper we are going to start with. For those of you that are joining us online, welcome to all of you. And thank you for being with us. Now, I'm going to ask, for those of you who have not yet subscribed to our channel, what have you been waiting for? Please just go ahead and click that subscribe button. And we are going to be revising chemistry together today. And please do note that there is memberships. There are memberships that are available. And what we do on our memberships is that we'll give you all information with regard to bursaries. Please, guys, I think one of you has a mic on. So if you can just mute your mic, thank you very much. Right, so we've got information in relation to our bursaries. We've got information that will assist you, but we also run 2 lives like this on a weekly basis for one for maths and one for physical science. So without any further ado, I hope that you guys are ready, willing and able. So what I'm going to be covering during the course of this live is firstly the section that I didn't go through the first time around. Now, the biggest section, guys, in chemistry would be your, organic chemistry, right? That accounts for about 33% of your chemistry exam. So that is quite a huge chunk. So I would ask you to please dedicate a lot of time there. What I will take you guys through though today is just the reactions in organic chemistry. That's the first part. And then we are going to skip through to rates of reactions. We're going to look at chemical equilibrium. And I think I might just touch on acids and bases. I don't think I touched on it the last time. Some of you it may not be included in your final exam, but I will go through that as well. All right, if you are ready, please tell me that I am ready. I've got a slight bit of a headache today because I had a hectic day, but hopefully you guys will bear with me. All right, and let's get through this together. All right, guys, are you ready? All right. Yeah, so if there are any questions, you should let me know. Right, so I'm taking the 2025 exam, May-June 2025. And in this case, I wanted us to start with question 4. Please confirm if you can see my screen.
Yes, sir.
All right, beautiful stuff. Right, now they say to us in the flow diagram below, we've got a primary alcohol P, which is used as a starting reactant to form different organic compounds under different reaction conditions, right? So here it is, we are starting with a primary alcohol. And we are taking that reaction, we are taking that alcohol through an elimination reaction, there it is there, for it to form compound Q. Now I can already imagine that compound Q must be an alkene. So when we take it through an elimination reaction, we are going to remove the OH, the hydroxide ion, together with one hydrogen, and in this case we are going to form an alkene in the process, right? And then what they do is that in reaction 2 we are taking that alkene and that unsaturated hydrocarbon, we are now going to form butane. So that tells me that must have been, in this case, but1-ene. Why am I saying but1-ene? Because remember, in this case, in fact, it was but2-ene. Let's see, we'll have to determine that. I think it was but1-ene, so we will remove, actually it was a primary alcohol, yeah, so it would have to be but1-ene, and I'll show you why just now. Okay, right, so that's but1-ene. So we take it through a reaction, so in this case hydrogenate that and it forms butane, right? The reason why I know that it was but1-ene is because the only way that you could have formed butane in this case is by simply hydrogenating that alkene, right? And then reaction 3, so we said primary alcohol. Now we can already predict what alcohol it was, right? Can anyone tell me what alcohol it was? So that would be butane-1-all. How do I know this? Because there we've got butane there that was formed from that. Are you guys with me so far? Guys, are you okay? All right, beautiful stuff. So we take also that but1-ene and we are going to hydrate it, right? React it with water. And in this case, I presume what we will now be able to form is butane, actually it would be butane-2-all. Okay, and I'll show you why in just a bit, because we would have now applied Markovnikov's rule. Okay, right, now let's go through the questions that we have there. They say what type of addition reaction, so we know it's an addition reaction. What type of addition reaction, write down the type of addition reaction represented by reaction 2. Okay, so what type of reaction, addition reaction is that? That would be simply hydrogenation, right? So we took an alkene and we reacted it with hydrogen, and so that would be hydrogenation. Okay, right, and then they say what type of elimination reaction represented by 1. So what did we do in number 1? We removed the H and the OH, right? So we are removing in essence H2O. So this would be dehydration reaction. Okay, right, which means that water would be a byproduct there. All right, now let's look at the next question. They say write down the IUPAC name of compound P. So guys, I want you to please note, they did say it is a primary alcohol, right? And I note in this case that that primary alcohol gave us reaction 2, which resulted in butane. So which other primary alcohol could it be? It can only be butane-1-all. Remember, you need to give the number or the location or the position rather of where your hydroxide ion would be, and that would be at carbon number 1. Okay, right, now let's go on to the next question. They say consider reaction 3, right? Now they say to us write down the balanced equation using condensed structural formulae, right? So we're looking at reaction number 3. So what would have happened in this case? We took an alkene and we are reacting it with hydrogen, we're hydrating it with H2O, and in this case it would form that alcohol. So we would have taken CH3, CH2, CH, and CH2. Now remember This would be an alkene, right? So remember that the carbons, the terminal carbons there, would have an insufficient number of hydrogens, right? So if you think about what that looks like in structural form, and if need be, you need to actually draw it out so that you can see what that looks like. So what do I have there? I've got a double bond that is formed. I've got hydrogen and hydrogen. And in this case, I've got here another hydrogen. So I've got CH3, right, with 3 hydrogens over there. I've got CH2, which is this one over here. I've got CH, which is there. And I've got CH2 at the end. Of course, in condensed structural form, I wouldn't have shown that double bond, but we know that it exists. And then we are reacting it with H2O, water, right? And in this case, what are we going to form there? We're going to form CH3. Now, please, I want you to note. So we are going to apply Markovnikov's rule. And what does Markovnikov's rule actually state? It says, well, in an addition reaction, right, the hydrogen will be added to the carbon with the most number of hydrogens. So I know that the hydrogen, we've got H2O, so we are going to add H and OH, but the hydrogen will go to the carbon that has the most number. So meaning that the hydrogen will go to the carbon at the end, and that's why I end up forming a secondary alcohol. So the OH will actually sit in the second carbon, right? So I've got CH3, CH2. So in that second carbon, now I'm going to have CH, OH, okay? I don't have as much space, so I'm going to try and make this arrow shorter. So that's CH3, CH2, that's CH. I can form an OH over there, or you can say CHOH, and finally I would have CH3, just like that, okay? Right, so please note, guys, it is very important for us to show in this case that it is a secondary alcohol that has been formed. Right, now they say to us, write down the name or formula of a suitable catalyst, okay? So what are we forming there? We are adding this with water, okay? So what we would actually use there as a suitable catalyst, you can either say we've got platinum that we are using, or in this case, we can even use iron as a catalyst. So in that case, that is what we are going to use, okay? Right, so the next question, they say, the name butane rather can be converted to compound P. So where's compound P? Okay. Oh yeah. So they are taking butane, right? So a saturated hydrocarbon, and we now want to convert it to an alcohol, right? Now they say to us, in a two-step reaction, right? Use structural formulae to write down a balanced equation for these two reactions. Now, we want to take butane, they said in structural form. So the first reaction that would happen, we've got butane over there, a saturated hydrocarbon, and we are going to take that. Now, what do we need to do first? We want to convert it firstly into a primary alcohol, right? So what we would need to do, and they did say that it is a two-step method, right? So what we are going to do, guys, is perhaps take it through an elimination reaction first, right? And what we are going to do is have an elimination reaction, right? And in fact, let's see. So if we take that, we're going to end up with an alkene. Okay, I end up with an alkene. All right, so there we go. Right, but remember, what did we eliminate? We eliminated hydrogen, okay? Right, and remember this is, this reaction happens in the presence of platinum, and of course, we have to say delta H as well there, okay? Right, so we are dehydrogenating, okay, this alkene, and we are forming an alkene. And so what I'm going to do is we can then now hydrate this, okay? So we can say, all right, so we are now going to take this guy over here. Okay. Right, so with an alkene, my only issue over here, perhaps I need to think about this a little bit. My only issue with this reaction is that if I hydrate this guy, we actually end up with, or rather the major product of it would give us compound S, okay? Whereas we wanted to have compound P in this case, which is the minor product, so with one of them. All right, we'll come back to it, guys. Let me just also just think about it a bit for the sake of our time. This is the closest one that I can think of, and it would give us a primary alcohol. But rather, so the secondary part of it would give us, or rather, let me say the major product would give us a secondary alcohol. Yeah, I'll think about how we can also write down perhaps a way in which, I'm just thinking at the top of my head, if we were to react this perhaps with sodium hydroxide, yeah, that would tend to make a primary alcohol. Yeah, I think we'll come back to this. Let me think about this quite thoroughly, okay? Right, but I'm thinking to myself that if I'd want to use the sodium hydroxide route, that would form in fact, yes, that's exactly it. That's exactly it. In fact, let's go back to it. Yeah, I think that would work quite well. So, what I would do is take an alkane, all right, and yeah, let's see, if I were to react this with sodium, in fact, I'm actually thinking about a haloalkane in that case. Yeah, I think I'd want to stick with the one that I just did just now. All right, perhaps I'll think about it if perhaps there is something else that we can have. Right, so the next one, they say to us, write down a balanced equation using molecular formulae for the complete combustion of butane. So again, what are we doing? We are writing it in molecular formulae, right? Note the previous one was in structural formulae. So what is butane in this case? Butane is C4H10, and it now reacts with oxygen. And what are we going to form? We're going to form carbon dioxide and water, right? So that would be a complete combustion. But what we need to do is make sure that we balance out this reaction. So this is going to be 4 carbons. So that's 4 carbons on this side. That's 10 hydrogens. So that would be 5 multiplied by 2, which would give us 10 hydrogens. Okay, excuse the noise there. There are some cars that are passing. Okay, so that would be 10 in this case. That would be 10 hydrogens. However, let's make sure the number of oxygens would be the same. So 4 multiplied by 2 will give me 8 oxygens, and 5 multiplied by 1, that will give me 5. So 8 plus 5, that's 13. So that means you've got 13 over 2 oxygens, okay? Right? Because 13 over 2 times 2 will give me 13. However, we cannot have a fraction as our coefficient. So let's multiply everything by 2. So that means if I multiply everything by 2, I would have 2 here. 13 over 2 times 2 gives me 13. 4 times 2 gives me 8. And 5 multiplied by 2 would give me 10. So that would be the balanced reaction for the complete combustion of butane. Okay, right. I just need to still settle down a little bit, guys, because I was on the road, actually just driving as fast as I possibly could. Okay, right. Are we all okay so far, guys?
Yes, sir.
All right, beautiful stuff. So here's what I want us to do. I want us to go quickly into question 5. That's on rates of reactions. And please don't be afraid to stop me anytime when I've started so that you can, obviously, if there are any questions. Right, so they say to us, the reaction between magnesium carbonate pellets, all right, and excess dilute hydrochloric acid. Now, please, I want you to note, guys, that immediately when they say to me that we've got something that is in excess, what does it suggest? It suggests that the other reactant must be the limiting reagent. So what does that mean? It means that magnesium carbonate must be the limiting reactant. Does that make sense, guys? Right? So they say excess dilute hydrochloric acid is used to investigate the effect of concentration on the rate of reaction. So there it is, we've got our reaction over there. Okay, so they say to us the apparatus used for this investigation is shown below. So what are they doing? They are going to measure the mass of the contents together with the container. And in this case, as the reaction takes place, as we are going to be forming carbon dioxide and using up magnesium carbonate, that is going to decrease the mass of the container together with its contents. So I'm assuming that the mass that they are showing us there is the initial mass, okay? But let's go to the questions. So they say, define the term rate of reactions. Please, guys, once again, I'm going to appeal to you just like I did when we were preparing for physics. Please make it a point that you invest some time into ensuring that you understand, your definitions, okay? Because they account for 10% of your total mark allocation that is given. Right, so what is rate of reaction? Okay, that's the change in the concentration of your products formed per unit of time, or you can say the change in concentration of reactants used with time, right? Now they say write down one controlled variable for this investigation. All right, so what are we changing? First of all, what will be remember we've got what are the two variables, Gonje? Here's the name trying to escape me. So we've got what's the word? I'm looking for the word. Please remind me, guys. The independent variable. Oh, I don't know how I forgot that. The independent variable, right? Right. So what would be our independent variable in this case? What are we changing? They said to us, look, we are changing investigates the effect of concentration on the rate of reaction. So what are we going to be varying? We are going to be varying the concentration of, the concentration of hydrochloric acid, right? And check how will the rate of the reaction. So what do we need to ensure remains the same? Talk to me. Can we say the mass magnesium carbonate, right? We definitely need to make sure that remains the same, isn't it?
Yes, sir.
We can also say the temperature of the reaction, isn't it? The initial temperature. Or, in this case, you can also state the state of division of magnesium carbonate. Okay? Right. So you can choose amongst those options. Okay, guys? Right. Okay, let's go to the next question. They say 3 experiments using different concentrations. So there it is. We are varying the concentration for each and every one of them, right? So 3 experiments using different concentrations of hydrochloric acid, right, are carried out. The concentration of hydrochloric acid during each experiment does not change. Okay, right. So here's what we want to do. Right. So they are actually just telling us what it is that we kept the same, right? They said the concentration of each experiment does not change, right? So they are telling us in this case for experiment 1, we use 0.1. For experiment 2, we use a higher concentration of hydrochloric acid, as well as experiment 3, we used an even higher concentration. Now they say to us the incomplete graph of the results of the experiment is shown below, okay? And they say give a reason why the mass of the reaction, the mass of the reaction mixture and flask decrease, okay? Why would the mass decrease? Because we are using up magnesium carbonate. Or you can say because we are forming hydrogen which escapes into the environment. Okay, does that make sense, guys?
Yes, sir.
All right, beautiful stuff. Okay, so they say for curve B, so we are definitely going for curve B. Calculate the average rate at which carbon dioxide is produced, okay, for the first 120 seconds, right? And they want us to measure that in cubic decimeters per second. Now, very, very important, guys. Right. Now, what do we have in the reaction? We know we started with an initial mass of carbon dioxide, the container together with its reactants, right? But what does the decrease in mass actually signify to me? It's telling me that the amount of magnesium carbonate is actually decreasing. Now, let's look at the first 120 seconds for graph B, right? We started with an amount of 144, and within 120 seconds, we are now at 143.87. That's the decrease in the amount of magnesium carbonate, right? So I can say, well, look, let's find out the change in mass. In this case, that's going to be 144.50, right, minus 143.87. Okay, let's find that out quickly. So 144.5 minus 143.87. Right, so I found out that the decrease in mass was 0.63 grams. Okay, now I want you to keep in mind, guys, what do they want me to actually calculate? They wanted me to calculate the average rate at which carbon dioxide is produced, but they want me to calculate that in cubic decimeters per second. Okay, so now I need to first find out how many moles of magnesium carbonate were used, right? So I'm going to say for magnesium carbonate, number of moles is mass divided by the molar mass. So that's 0.63. Now, where am I going to get the molar mass? I'm going to have to go to the periodic table, right? So if I go to the periodic table very quickly, right? So magnesium, there it is. That's 24, right, in my periodic table. And it's magnesium carbonate. So we've got carbon, which is 12. We've got oxygen, which is 16, right? And what's the formula for magnesium carbonate? Okay, I'm just going back to my question, right? So what's the formula for magnesium carbonate? Okay, there it is. It's MgCO3. So that means I have 24, that's magnesium, plus, in this case, carbon, which is 12, plus 16 multiplied by 3, which is for oxygen, right? Okay, so let's calculate that quickly. So I'm going to say 0.63 divide by, I've got 24 plus 12 plus 16 multiplied by 3. Right, and that gives me 0.0075 moles, right? So remember, when we are doing stoichiometry, we always need to convert to moles, right? So these are the number of moles of magnesium carbonate that I have used. Now let's go into our reaction and check what is the ratio of magnesium carbonate to carbon dioxide. So for every 1 mole of magnesium carbonate, I will form 1 mole of carbon dioxide. So what does that say to me? Any number of moles of magnesium carbonate that I use, I will use an equal number, I will produce rather an equal number of moles of carbon dioxide. So what can I therefore say? So therefore, the number of moles of carbon dioxide that are produced will also be 0.0075 moles, right? Why? Because for every 1 there's 1. So meaning if there's 10, there'll be 10. If there's 0.0075, there'll be 0.0075. So for every 1 there is 1. So now we've got the number of moles of carbon dioxide. But remember, what are we looking for? We are looking for this change in terms of volume, right? In terms of volume. So I'm going to have to find, in this case, the volume rather of carbon dioxide. So I'm going to say volume, or rather let's say number of moles for carbon dioxide. That's volume divided by the molar volume, right? So I'm looking for volume. So that means number of moles is 0.0075. I'm looking for volume. The molar volume is given to me as 24.5 cubic decimeters per mole. And so what would be my volume? If we cross multiply, in this case, we've got 0.075. Okay, we're going to multiply that by 24.5. What does that give me? It gives me 0.18375 cubic decimeters. And here's what I want you to note, ladies and gents. So to calculate the rate of reaction, that's going to be change in volume divided by the change in time. What is my change in volume? My volume change from 0, right? So that's 0.18375 minus 0, and that's divided by the change in time. That would be 120 seconds. And in this case, what would be my rate of reaction? Okay, so I'm going to take that amount and I'm dividing it by 120, and I get an amount of 0.00. In fact, maybe let's convert that into let's convert They said per second, right? Yeah, it is 120 seconds. I'm going to convert that into scientific notation. So that gives me 1.53 times 10 to the power negative 3, and that is cubic decimeters per second. Okay, I hope you're with me on this. So let me just outline what I did. Firstly, I calculated the change in mass, right? But what is that change in mass for? That is the change in mass for the amount of magnesium carbonate, right, that was used. And I converted that into moles, right? And in this case, when I converted that into moles, I then found out the number of moles of carbon dioxide, right? Because it's 1:1. Then we found, in this case, the volume of carbon dioxide that was produced, and therefore we calculated the rate of the reaction. Okay, right. So that would be the way we go about that question. Quite an interesting question, I must admit. Right. Now, they're asking us a question. Which curve represented experiment 1? Choose from A, B, or C using the collision theory to explain your answer. Now, let's go back into this. So, experiment 1 has got the lowest concentration. So, in this case, it would have the lowest rate of reaction. Which one has the lowest rate? Within the 120 seconds, you've got, in this case, the lowest amount of change in the reaction. So this would be for experiment 1. That would be for experiment 2. It's got a higher rate of reaction, right? But the highest rate of reaction is actually this one, where the concentration is the highest. Okay, right. Now, how do we explain this? So they said to us, which one is experiment 1? That would definitely be graph A. Okay, now, how do we explain that in terms of the collision theory? If you don't mind, I'm just going to remove this. And guys, please, if you don't mind, I'm not going to be as exhaustive in writing all of this down in detail, right? So what are we going to say, right? So we're going to say the lower the concentration, okay, the lower the concentration of HCl, okay, the lower, or rather the lesser the moles per unit volume, right? So the lesser the number of moles per unit volume. Okay? Now, what does that mean? It means that there'll be less moles that have sufficient kinetic energy, less moles that have sufficient EK, and sufficient EK rather, kinetic energy, and correct orientation. Okay? And that would decrease the number of collisions, of effective collisions per second. Okay? Per second. And that would decrease the rate of the reaction. Okay, so that means that when I look at those graphs, definitely graph A has got the lowest, in this case, the lowest amount.
Sir,
Yes. Say that again.
May you please repeat the second point?
The second point.
Yes, sir.
Okay, I said, okay, so firstly I said the lower the concentration of hydrochloric acid, right, the lesser the number of moles per unit volume, right? Okay, so less moles have sufficient kinetic energy and correct orientation, right? So there are less moles that have sufficient kinetic energy and correct orientation, and that will decrease the number of effective collisions per second, and that will decrease the rate of reaction. Are we good? Are we all good in the hood?
Yes, sir.
Yes, sir.
All right, beautiful stuff. Okay, and for those of you that are online, I hope that this makes sense. Okay, let's go on to the next one. They say to us, how will the final mass of carbon dioxide produced in experiment 2, all right, compared to that of experiment 3, choose more than, less than, or the same? Okay, give a reason for the answer. Right, now here's what I want you to note, guys. In as much as they didn't complete these graphs, okay? Now what I want you to please note is that we've got the same amount of magnesium carbonate, right? And it is the limiting reagent. So what that does is that despite the fact that our concentration for hydrochloric acid is different, but we'll still produce the same amount of carbon dioxide. Why? Because magnesium carbonate is the one that is limiting the reaction, right? So the answer to that is that it will be exactly the same, right? It will be the same, right? Why? Because magnesium carbonate is the limiting reagent. Okay, so I'm going to remove this so that you can see that. So magnesium carbonate is the limiting reagent, and therefore, it will determine, the amount of carbon dioxide that will be produced. The amount of CO produced, okay, or CO2 rather, that will be produced. I hope that's clear, guys. I need to move on from this question, and that would have been a whopping 17 marks, guys. Really, this is one of those sections that you really want to maximize on. It carries quite a huge amount of weight. Okay, right, so for the sake of our time, let's go on to question number 6. Right, now they say to us, the reaction between powdered carbon, okay, and carbon dioxide, which is CO2, takes place in a closed 3 cubic decimeter container, all right, according to the balanced equation below. Right, so there it is there. Right, now they say to us equilibrium is reached at temperature T. Right, so they say the graph below, not drawn to scale, right, shows the curve for the mass of the reactant in the container against time. So here's what we have here, right? So we've got carbon dioxide rather. So we started with an amount of 41.2, but that's grams, right? And whereas we started with an amount of carbon which is 14 grams, okay? Right, now they say to us, how will each of the following changes affect the number of moles of carbon dioxide at equilibrium? So we are applying Le Chatelier's principle here. So they say to us, choose increase, decrease, or remain the same. Right. Now if a catalyst is added, right? So remember that a catalyst will not shift equilibrium either to the left or to the right. So we know that in this case, it would just simply remain the same. Okay. It would remain the same. All right. Now they say to us, the volume of the container is increased at a constant temperature. Now, remember guys, when we're looking at volume, or rather when we're looking at, the volume of the container is increased. So we are going to look at the reaction and ask ourselves, how many moles in this case do we have, of gases rather, do we have on the left-hand side? Now look at this. This is not a gas, that's solid. So how many moles of gases do we have? We've got only 1 mole of gas. So we've got 1 mole over here. How many moles of gases do we have on the right-hand side? We've got 2 moles of gases, right? Now when I increase the volume, okay, I am making the space bigger, okay? Now if I make the space bigger, equilibrium will shift to the side that occupies more volume, the side with a bigger number of moles. So which means I will actually favor the forward reaction. So that means that more carbon monoxide will be formed, and that means carbon dioxide will actually decrease, right? So my answer there will be decrease. So for this one, the amount will decrease. Let me explain that again. So what did I do? I increased the volume of the container, meaning that I decreased the pressure. So when I increase the volume, I make the space bigger. Equilibrium will shift to the side that occupies more volume, the side with the most number of moles. In this case, that's our right-hand side. So equilibrium will shift to the right. And so as a result, more carbon monoxide is formed. And in this case, that would decrease the amount of carbon dioxide, which is what they asked us about. Okay, right. Now, and of course, if you had to increase decrease the volume, that means increase pressure. Obviously, you favor the side that occupies less volume. Right, now they say to us, more powdered carbon is added. Now I want you to note, guys, by adding a solid or a liquid, right, in this case, that will not affect equilibrium in any way, right? So it's only when we increase concentration, that is gases and aqueous solutions. So this will also remain the same. Okay. Right, it may affect the rate of the reaction, but in this case, it will not affect equilibrium in any way. Right, now let's go to the next question. They say explain the answer to question 6.1.2 by referring to Le Chatelier's principle. All right, so they wanted the answer to this guy over here. Right, so what are we going to say? Exactly what I had explained to you. Right, that an increase in volume, okay, will shift equilibrium to the side, that occupies more volume. Okay, so you've created more space. Equilibrium says, no, we don't want that. So it will shift to the side that occupies more volume. It will try to fill up that space as much as possible, right? Equilibrium will shift to the side that occupies more volume. Occupies more volume. Okay. So equilibrium will shift to the right. Okay. So equilibrium, or you can say equilibrium will favor the forward reaction, or you can say the forward reaction is favored. The forward reaction is favored. Sorry guys, I'm going to have to write in abbreviated form. Okay, and as a result, that is why we said that will decrease the amount of carbon dioxide. Note that the question asked us about carbon dioxide. Okay, so that is very important for us to note. All right, now let's go to the very next question. They say to us, calculate the value of X as shown on the graph. Okay. Right, now guys, I want us to note in this case, I'm going to kind of draw our table right here because we're going to need it anyway, right? We're going to need our table. So our rise table, I'm going to write it or draw it there. Right, let's write down what we have. So we've got carbon, we've got carbon dioxide, right? And if you don't mind, guys, please remember, you will write there initial, that would be in moles. Check, it is in moles. That's change, that's in moles. That's equilibrium in moles, as well as equilibrium concentration. That would be in moles per cubic decimeters. And I am also mindful that there are those of you who prefer to write down the ratios, right? Nothing wrong with that. I just put the ratios onto the actual as coefficients in this case. So I've got CO. So my ratios, there they are. That's going to be 1 over here, that's 1 over there, and that's 2 over there, right? Okay, so how much did we start with? Now this is very important. I'm going to come back to this in just a bit. So we started with 41.2 grams of carbon dioxide. So how do we get that number of moles? Number of moles is mass divided by molar mass. So how much did we use? Right, so that's going to be 41.2 grams divided by, so I'm actually, because I know they are going to ask us about equilibrium constant, we might as well just get through this, okay? So 41.2 grams divided by the molar mass, in this case, from the periodic table for carbon dioxide, right? Okay, we'll come back to carbon in just a bit. So for carbon dioxide, that's 1 carbon, which is 12, plus 2 oxygens, that's 16 multiplied by 2. So that will give us 44, right? So, are we still there, guys? So 41.2, and this is divided by 44. That would give me 0.9, okay, I'll say 0.94 moles, okay, right. So I'll say for carbon dioxide, we started with 0.94 moles. And then what do I notice in this case? What about carbon? So we started with 14 grams of carbon. So number of moles, that's 14 mass divided by molar mass. What is the molar mass for carbon? That would be 12, isn't it? So that would be 14 divided by 12. Okay, that gives me 1.17. Okay, so we started with 1.17 moles. Now remember, right at the beginning, we had not formed anything in terms of carbon monoxide, right? So in this case, I'm going to leave it there. Right, and then what do I notice on my graph? They give me the equilibrium values, but I do not know what the equilibrium value of carbon dioxide is. However, I do know what the equilibrium mass of carbon is, right? So equilibrium value of carbon is 4,44. So I will say, okay, for carbon, that would be 4.44. Again, divided by 12. So let's do that quickly. Divide by 12, that would give me 0.37, okay? So at equilibrium, the amount of carbon that I have is 0.37. Now, here's what we are going to do, guys. In order for us to get the amount of carbon dioxide, I'm going to say, well, I started with 1,17, right, for carbon. And at the end, I've got 0.37. How much did I use? So you subtract those two because that's your reactant. Yes, please go ahead and ask.
So why are you using the carbon?
Why am I using carbon? Because that's the one that I have initial for, right? Look at that graph. I've got initial and I've got final value. Can you see that? Okay. Does that make sense to you?
No.
Okay.
It's what confuses me because it's in solid form.
Because it's in solid form. But do you agree with me? In this case, despite the fact that it's in solid form, it formed part of this reaction. What we are not going to be doing is including it as part of our KC calculation, right? But it doesn't mean that it didn't participate in the reaction.
Okay, I understand.
Does that make sense? So remember, if it's in solid form, it doesn't mean that you're not going to include it in the table, right? But what it does mean, can you say that again?
I got you said so please repeat.
Oh, I said the fact that it's in solid form does not mean that we are not going to include it in the table, right? But
Okay, sir.
where we are not going to include it is when we now calculate the equilibrium constant. So we're not going to include it when we are calculating Kc in our equilibrium expression. Does that make sense?
Okay, sir.
All right. Okay. And by the way, it's the only one that we've got the most information out of either way. Okay. Right. So we said we've got 1.17, and at the end we've got 0.37. So how much did we use? We used 0.8. Does this make sense to all of us, guys? So what this means, remember, we only use our ratios where it pertains to the change in moles. So we're going to say, all right, for every 1 mole of carbon, I use 1 mole of carbon dioxide. So what does that mean? For every 1, there's 1. So when I use 0.8, I'm also going to use 0.8 of carbon dioxide. And then look at carbon monoxide. For every 1 mole of carbon, I get 2 moles of carbon monoxide. So what does that mean? If I use 0.8 of carbon, then how many moles of carbon dioxide? I'm going to get twice as much. So this will be 1.6. 0.8 times 2 will give us 1.6. Does this make sense to all of us, guys?
So repeat the sheet.
Say that again.
Repeat the first thing.
Okay.
We added the 1.6.
Oh, okay. So repeat the part for the 1.6.
Yes, sir.
All right. So for every 1 mole of carbon, I am going to use I'm going to produce 2 moles of carbon monoxide, right? So for every 1 person, there's 2 legs, right? So if there's 4 people, how many legs are going to be there?
16.
Man. For 1 person, there's 2 legs. For 4 people, how many legs?
Oh, 8.
8. Okay. Yeah. So you're going to get twice as many, right? So what I'm saying to you is that if you look at carbon, we had 0.8, right? So how many moles of carbon monoxide are we going to get? So when you cross multiply that, you'd be able to get the answer. N times 1 will be N. 0.8 times 2, that will give you 1.6. So which means the number of moles of carbon monoxide that you're going to produce, my eyes are a little bit irritated. So the number of moles of carbon monoxide that you're going to produce would be 1.6. Does that make sense, guys? Twice as much as we did, right? Right, now let's go for it. So now, remember the question, what are we looking for? We are looking for the value of X. What is the value of X? That is the number of, in fact, the mass of carbon dioxide at equilibrium. So now look at what we did for carbon dioxide. We started with 0.94 moles. We used 0.8. How much would we have at the end? So we're going to say 0.94 minus, because that's a reactant, right? Minus 0.8, and what will that give us? 0.14. Does this make sense to us, guys? Okay, right. So now, can we get the mass of carbon dioxide at the end? So, number of moles is mass divided by molar mass. But for me to get the mass, I'll say mass is number of moles times molar mass. The number of moles of carbon dioxide that I have at equilibrium is 0.14. So that will be 0.14 multiplied by, in this case, carbon dioxide is 44. So that will be multiplied by 44. And what do I get there? So 0.14 multiplied by 44 grams per mole. Remember, we calculated that in grams per mole. And so that means the mass should be, so X should be 6.16. And that's in grams. Are we all together, guys?
Yes, sir.
All right. So we got the mass there. Now, the next question says calculate the equilibrium constant. So I'm going to have to complete the table so that we can calculate the equilibrium constant. Right. We started with nothing for carbon monoxide. We produced 1,6. What would we have at equilibrium? We would have 1,6. Okay, right. Now, here's the part I want you guys to please get right. Carbon is a solid, so you cannot quantify a solid in terms of concentration, right? It has its concentration is constant. Okay, so that you don't confuse yourself. And also include it in the equilibrium expression. Please just cancel out carbon. Okay, so that's what I was saying, that we are not going to include carbon in the equilibrium expression. However, we are going to include it. It did take part in the reaction. All right, so what's our volume? Our volume is 3 cubic centimeters. So we're going to have 0.14 divided by 3. As well as 1.6 divided by 3. And so in this case, if you don't mind, I'm going to leave it in that format. Okay, so what's our Kc expression? It's the molar concentration of our products. Our product is carbon monoxide, but our coefficient is 2, so that would be squared, divided by the molar concentration of carbon carbon dioxide. So that would be carbon dioxide. Okay, so let's calculate that. What's the concentration there? So that's 1.6 over 3. Let's say 1.6 over 3 all squared divided by carbon dioxide, in this case, we said was 0.14 over 3. Okay, right. Please can you calculate that for me as quickly as you possibly can? Okay, so we've got 1.6 over 3. Now 1.6 divided by 3. This is all squared, right? And I'm dividing this, rather divide by 0.14 divided by 3. Okay, I get a value of 6.1, can we say? Guys, please confirm if you get the same answer.
Yes, sir.
All right, beautiful stuff.
Yes, sir.
And so that is how we would have gotten our equilibrium constant. Okay, right. And then let's go to the last question here. So they say to us, we've got a balanced equation for this reaction. It's written below for easy reference, right? Okay, they say the graph below shows the equilibrium number of moles for carbon monoxide, carbon, as well as carbon dioxide at T1. So there's the graph that they are giving us. So they started the graph at equilibrium, right? All our amounts are constant, okay? Right. Now, if you look at this, they say to us, the graph below shows the equilibrium number of moles of carbon, okay, carbon monoxide, carbon, and carbon dioxide in the flask at T1. They say at T2, right, carbon monoxide is added to the flask. Now you can see this. We added carbon monoxide, and in this case it affected the amount at equilibrium, right? So equilibrium shifted. You can see that carbon monoxide would decrease, and in this case it didn't affect the amount of carbon. It is in solid form, and carbon dioxide in this case increased, right? Now they say to us, let's see, curve Z correctly shows the change in the amount of carbon monoxide between T2 and T3. Right, now a learner draws the corresponding curves, right, labeled X and Y for carbon, right, which is solid, and carbon dioxide respectively. Okay, so there they are. There's X and Y. Now they say which of these curves is correct, is the correct representation for these changes. Okay, right. Now they say choose from X or Y, or rather X or X and Y. Now if I look at, in this case, X, right, X wouldn't be correct. Why? Because we are talking in this case about the amount in moles. Would you agree with me that if I am affecting, so in this case what it's suggesting to me is that I increased this guy, right, carbon monoxide, it would favor the reverse reaction. So what happens? In this case, more of carbon dioxide increases. But remember, I can't just increase the amount of carbon dioxide without it affecting the number of moles of carbon. Do you guys agree with me? So graph X looks like it is not correct. Okay? So definitely the amount of carbon dioxide would be correct in that case. So definitely it should be graph Y only that is correct. Does that make sense, guys?
Yes, sir.
All right, beautiful stuff. And then finally they say, what effect will the addition of carbon monoxide have on the equilibrium constant? Choose increase, decrease, or remain the same. It will definitely remain the same. Remember that it's temperature only that affects the equilibrium constant. Okay, right. That was a whopping 19 marks. I hope that was clear. All right, and I want us to quickly jump because in this case at past I need to be closing this live. So I'm going to be going into, in this case, that's acids and bases. All right, I know that this is one of those really contentious sections, but I want you guys to please note, when it comes to acids and bases, not everything, is, around that 7 mark or 8 mark question. Usually it has to do with back titration, and there's a little bit of gymnastics that has to be done. So please don't panic around it, okay? for me, I think the most important thing is that you make sure that even on the theory sections of acids and bases, you're still able to hold your own. All right, now let's go for it. Now, they say to us, define an acid according to the Arrhenius theory. Right, now remember that the Arrhenius theory simply tells us that an acid is a substance that is able to donate hydroxide ion, right? In this case, we know that when you look at the Arrhenius theory, so two things that emerge, right, is that when you look at an acid, it's an H plus donor in this case, and a base is a hydroxide ion donor. Okay, and that's why, according to the Arrhenius theory, whenever you react an acid and a base, you will always get a salt and water. Okay, so in this case, but that's not the whole definition. All right, let's go for the next question. So they say to us, the table below shows us the aqueous solution of different substances, right, each with a concentration of 1 mole per cubic decimeters at room temperature. Right, now firstly they say identify from the table, okay, and write down the formula of a weak diprotic acid. Okay, so remember, a diprotic acid is one that is able to give us two hydronium ions, right? In this case, so what would I... Yes. Excuse me? You can't see what?
Sorry, he just came back, sir, but I couldn't see what you were doing, sir.
Why can you not see it?
I don't know, sir. You should just bring it out. It's back now.
Okay, I'm not too sure what you mean by that. Okay, are you guys all okay?
Yes, I think he meant he couldn't see the slides for a couple of moments and then it came back.
Oh, okay, all right. Okay, I hear you. All right. Yeah, so if it does that, it might be network on your side, ne? Okay. Right. Okay, so they say to us, we want a weak diprotic acid. Now remember, there are two diprotic acids here. The first one would be sulfuric acid, right? It's got two of those hydronium ions. Another one would be oxalic acid. But remember, sulfuric acid is actually a strong acid, but we want a weak one. So that would be definitely oxalic acid. Okay. It is diprotic, but in this case, it's a weak acid. Right, and then they say a solution with a pH of 7. So, with a pH of 7, it means that it comes from a strong acid and a strong base, and that would definitely be sodium chloride in that case. Whenever you are taking hydrochloric acid plus, in fact, sodium hydroxide, that would give us sodium chloride. So that has a pH of 7. So that would be NaCl. Okay. Right. Now they say to us an ampholyte. Remember, what is an ampholyte? It's a substance that can behave as both an acid as well as a base. Okay. Now, if you look at it, whenever you've got an ion, right, that has a hydrogen in it. So look at this guy. So it can receive an H plus and still become H2CO3, but it can also give away an H plus and become CO3 2 minus. Okay, so that would definitely be an ampholyte. So that would be HCO3 minus. Okay, that would be an ampholyte in that case. Everything else is either a salt, an acid, or a base. And then they say to us, the solution which when neutralized with oxalic acid, right, will have a pH that is greater than 7. Now remember, you've got a weak acid over here, right? So if I take a weak acid with a strong base, okay, I will get a basic salt. So if I take a strong base with a weak acid, I get a basic salt. In this case, it would have a pH which is greater than 7. So which one is my strong base? So I can take the sodium hydroxide. I think I can also take magnesium hydroxide as well. So I would say sodium hydroxide. Okay, right. Are we all okay so far, guys?
Yes, sir.
All right. Okay, so let's go to the next portion of this question. So they say to us, an unknown acid, which is HXY, is investigated. During a titration, they say 23.64 cubic centimeters of a 0.11 moles of this acid, right? Solution neutralizes 20 cubic centimeters, okay, let's say of, rather 20 cubic centimeters of a 0.26 moles per cubic decimeters of this solution, right? Now, of a sodium hydroxide solution. They say calculate the value of X, all right? And hence write down the formula, the balanced equation for this reaction. Now, I want us to do this first. So if we were to take, now please I want you to listen very carefully, guys. So for instance, if I were to take, let's say, sodium hydroxide with this acid, HXY, okay? In this case, what's going to happen in this case? So I am going to form sodium with Y, right? And in this case, I'm going to also form H2O, okay? Right, now I want us to note in this case, for us to be able to balance this, we would need to know what X is. All right, are you guys with me so far? Right? I would need to find out what is the value of X. Okay? So, all right, are you guys with me so far? Does that make sense? Okay?
Yes.
Right. So I would need to find out what is the value of X. Now let me make an example. So for instance, if I take sodium hydroxide with H2SO4, I'm making an example with this, with this guy. So what does that give me? It would give me sodium sulfate, okay? Right? So the number of moles of sodium in this case would be determined, or rather the number of atoms of sodium that would form on the other side would be determined by the ion that is formed over there, right? And this is plus H2O. But again, what do you need to do? You still need to balance out this formula, okay? Right, and I'm taking you somewhere with this. Okay, so if you look at this, so which means the number of moles of sodium ions that would be formed would depend on what X is, right? And I'm coming back to this formula at the top. Okay, sodium with Y, okay? Right, now look at how when I balance this out, look at what it's going to do, right? So in this case, I need to now make the number of moles of sodium, right, to be twice there. And that would make my formula somewhat balanced. But look at this, also 2H2O. Can you guys see that? No? So by virtue of having this guy here, it has kind of determined how many moles I would have had to have for the reaction. Now, I want you to please stay with me. Okay, please stay with me on this. Right, so when I look at this, firstly, it means the amount of sodium, right? So sodium X, right? You remember we had a 2 here, right? So sodium X, and what determined that? It's this amount here. So sodium X, whatever Y is. Are you guys with me now? Right? But what did that do? Right? We know we've got H2O over there. But what did that do? It now changed the coefficient of my sodium hydroxide. All right? So that became X. Okay? That it became 2 over there. But now it will become X because it's unknown. And it changed that to 2. So that will also become X over that side. Are you guys with me so far?
Sir, please repeat over the X.
Okay, right. Let me go back again to this, right? I'm making an example with sodium hydroxide with sulfuric acid, which is a diprotic acid, right? If my acid is diprotic, what did it do? Right? It made, firstly, okay, let me go back to this. Okay? I don't mind taking a bit of time on this one. Okay, so if my acid is diprotic, so let's say we've got sodium hydroxide plus H2SO4. Okay? What do we get on the other side? Sorry, I'm just scrambling a little bit for space. So sodium hydroxide plus H2SO4. What did that do? Right? It gave me on the other side, I will get sodium 2 because sodium has got a valency of 1, right? But now I need 2 sodiums to be with my sulfate. Why? Because of that 2 over there, right? Again, I get plus H2O. So what will it do? Now to balance this reaction, I will need to place a 2 over there and a 2 over there. I'm showing you for sodium, for sulfuric acid, that by virtue of having that as diprotic, what it has done, it has affected the number of moles of sodium hydroxide I need. It affects the number of moles of water that I need. Are you with me now? So in this reaction that we've got sodium hydroxide plus HX rather, HXY. Okay? So what will it do? Remember I ended up with sodium 2 there. But because I don't know what X is, what will I end up with? I end up with sodium XY. Does that make sense? Okay. It was a 2 there. It became a 2 there. It's an X there, so it becomes an X over there. Does that make sense?
Yes.
Okay, right. But I've got plus H2O. So I've got plus H2O over there. So what happened? Because I had a 2 there, the coefficient of sodium became 2. But because I have an X here, the coefficient of sodium hydroxide will be X. Okay. Right. And of course for water, that will be X as well. And now please, I want you to note, I'm going to use the formula, right? CaVa over Cb Vb is equal to Na over Nb. And remember, what is my Na and Nb? these are the coefficients of my base. Okay, so this would be my base and this would be my acid. Those are my coefficients, right? So the coefficient for the base is x and the coefficient for the acid will be 1. Okay, so let's use what we've got over there. So Ca, what's the concentration of my acid? 0.11. So I've got 0.11. I'm going to be running out of space there. So 0.11 multiplied by the volume, which is 23.64, divided by the concentration of the base, 0.26, right, multiplied by the volume of the base, which is 20, is going to be Na, but what's my Na in this case? That's 1, right? What's going to be my B value? My B value is going to be, the coefficient for my B value is going to be x. So all I need to do is cross multiply over there, right? Okay, so I'm going to be cross multiplying. So I'm going to say, let me write it there, 0.11 times 23.64 times x. Okay. Multiplied by 0.64 times x, which is equal to 0.26 times 20. Okay. Right, so let's do that very quickly. So I'll say 0.26 times 20, right, divided by 0.11 times 23.64. All right, and look at the number that we get, 1.999. So what is x? X would be equal to 2. Does that make sense, guys?
Sir, can you please repeat it?
Okay, which part did you not understand?
From the point where you started with the calculations.
Okay, so I said, remember, what we've got there is the formula CAVA over CBVB, right? Which is NA over NB. So this formula we use for the titration, okay? So what did I do? I just substituted the values. In this case, when you use this formula, this would be the, remember this is our acid. So this would be the volume of your acid. This would be the concentration of your acid. This is sodium hydroxide. This is the volume of your base. This is the concentration of your base. So all I did was to substitute for the acid as well as for the base there, right? Now, where do we get the values for Na and Nb respectively? We take it from the coefficients. This is my base here, so that would be 2, right? That would be my coefficient for the base, right? And here, my coefficient for the acid, that would be 1. So if I was using that formula, that would be for the acid, that would be 1, and that would be for 2, right? But in our previous formula, for the acid we had 1, and for the base we had x. Are you with me now?
Yes.
Okay, and so all you just simply do is just plug in the Ca value and the Cb value as you have them appear over there. And what you got was that your value for x was equal to 1.9999, which is actually equal to 2. All right.
Okay, sir, thank you.
All right, beautiful stuff. Okay, so finally, guys, this is out of 9 marks. Shoo. We are almost, actually, we are out of time, but I'm still going to go through this question as the last thing that we are going to be doing. So please just stay with us if you are watching this. So they say to us, in an experiment, we've got 1.5 grams of powdered impure calcium carbonate sample, right? Right, so they say to us, is reacted with 200 cubic centimeters of this guy. Now note, this is impure, right? So which means we cannot use the number of moles to calculate for that guy. Right, so they say to us, right, it is used or reacted with 200 cubic centimeters of 0.15 moles per cubic centimeters of hydrochloric acid solution. Right, the balanced equation is given over there, and they say all the carbon dioxide formed escapes from the solution. Okay, now they say to us the pH of the solution, the resulting solution rather, has a pH of 1.61, okay, and a volume of 200 cubic centimeters, right? Assume that all the calcium carbonate in the impure sample reacted with the hydrochloric acid and none of the impurities reacted. Now, they wanted us to calculate the mass of the impurities in the 1.5 gram sample. Okay, right. Now, guys, this is one of those questions. And really for me, guys, you don't want to make this the crux of acids and bases, okay? You may get this question, you may not get it, but the reality is that, you know, there are just some certain things that you just would need to kind of know of. This is one of those level 4 type questions, if you ask me, but stay with me, okay? So firstly, where are we going to start? Okay, I can't use the 1.5 grams, so I need to find out with the amount that would have been formed in this case, right? They said to us, we took the hydrochloric acid in this case, right? And they said the resulting solution of that has a pH of 1.61. Now, what is that resulting solution? And now, please, guys, I want you to stay with me just a bit. So we've got some of the hydrochloric acid that reacted, okay? But we also have the hydrochloric acid that remains unused. So let me find out how much of it remained unused, right? So meaning hydrochloric acid must have been in excess, right? So the one that remained unused is the one that's now going to form this pH of 1.61. So let's find out how much of it was actually unused. So I'm going to say, well, pH. Now, stay with me. That's minus the logarithm of the hydronium ion concentration. Our pH is 1.61. So this will give me the amount of hydronium ions that remained, okay? And therefore that will give me the concentration of hydrochloric acid that remains unused. So remember, when I want the concentration of hydronium ions, that will be equal to 10 to the power minus pH. So that's 10 to the power minus 1.61. So let's get that value, okay? So that's 10, that's yx negative 1.61. Okay, right, so I get a value of 0.024, okay, let me say 0.025, if you don't mind. Now, what is this? This is the concentration of hydronium ions that still remain unused, okay? That remain in our resulting solution, okay? Now that I've got the concentration of hydronium ions, can I find out what the number of moles of it are? Of course I can, right? So the number of moles, that's concentration times volume. So that's 0.025 multiplied by the volume. They gave me the volume to be 200 cubic centimeters. So I will say, well, this is multiplied by 0.2. And remember, in this case, I'm converting it to cubic decimeters. So therefore, this is 200 divided by 1,000. And so 0.025 times 0.2, this will give me 0.005 moles. Now, guys, what is this? These are the number of moles of hydrochloric, or rather hydronium ions that remain in the reaction, right? After it has reacted, I just did something there. Sorry about that. Okay, after it has reacted, okay, I just need to go back to that. Ooh, it erased everything that I'd done there. All right, so we found it to be number of moles, that was 0.0025. Okay, I forgot whether it was 0.0025, but we can find it from our calculator. Yes, it was 0.005 moles. 0.005 moles of hydronium ions. Okay, now remember that hydrochloric acid, when it ionizes, gives us only one hydronium ion. So which means the number of moles of hydronium ions would be the same as the number of moles of hydrochloric acid. So therefore, it means that the number of moles of hydrochloric acid that remains unused will also be 0.005 moles. Now, I want you to remember this. What is this? This is the unused amount, okay? Or you can say this is the excess amount, okay? But how much hydrochloric acid did we start with? Okay, so they told me at the beginning the concentration was 0.15 and the volume is still 200, right? So this is now the initial number of moles, and I'm going to just change color. So the number of moles initially would be concentration times volume, that's 0.15 times the 0.2, okay? So this is the amount of hydrochloric acid that we started with. 0.15 times 0.2, that would give me 0.03. Now guys, I want you to please stay with me. So we started with 0.03 moles of hydrochloric acid, and at the end we had 0.05 that remains unused. How much of it must have reacted? So the ones that reacted, so the number of moles of hydrochloric acid that reacted would be 0.03, the initial, minus the amount that remained unused, 0.005. And so what am I going to get there? Okay, 0.03 minus 0.005, that will give me 0.025 rather, moles. Right. So the amount of hydrochloric acid that reacted is 0.025 moles. But what did hydrochloric acid react with? It reacted with the pure calcium carbonate. Okay? So, what do I note? For every 2 moles of hydrochloric acid, I will use 1 mole of calcium carbonate. So let me find out the number of moles of calcium carbonate. Okay, I just want to get some space somewhere. Okay, let me do this. All right, so that we can see that. So for every 2 moles, or rather for every 1 mole of calcium carbonate, I will use 2 moles of hydrochloric acid. So my question is, what would be the number of moles of calcium carbonate that would have reacted in order for me to use 0.025 Remember, that's the number of moles of hydrochloric acid that reacted, right? So let's find out quickly. So if we cross multiply, once again, 2 times n, that will give me 2n. 0.025 times 1, if we cross multiply again, that will give me 0.025. And if I divide by 2 on either side, so the number of moles of calcium carbonate that would have reacted would be 0.00125. So we divide that number, we divide 0.025 divided by 2, that gives us 0.0125. Now, for those of you that are on YouTube, all right, please, I hope that you are still tracking with me. Right, so what did we do? We found out the number of moles that were in excess for hydrochloric acid. We found out the initial number of moles for hydrochloric acid. Then from that, we determined the number of moles of hydrochloric that reacted, okay, hydrochloric acid that reacted. From that, we now determined, right, in terms of the ratio, how many moles of calcium carbonate actually reacted in that case. Now, we found that that number was 0.0125. Now, stay with me, guys. So, now that we've got the number of moles of calcium carbonate that reacted, I can get the mass. So the mass would be number of moles multiplied by molar mass. That's 0.0125 times the molar mass of calcium carbonate. But what is it? Okay? Remember, you take calcium plus, which is 40, right? Plus carbon, which is 12, plus oxygen, right? You've got 3 times oxygens. That's calcium carbonate. So that would be 100. Okay, so 0.0125 multiplied by 100, and I get 1.25 grams. Now, guys, what does this mean? It means that the amount of calcium carbonate that reacted, the pure calcium carbonate, was 1.25 grams. But how much was given to me? 1.5. So meaning the rest of it must have been impurities. They said to me, calculate the mass of the impurities. So how am I going to get that? Right? So the mass of the impurities would be equal to the total mass, which is 1.5, minus 1.25, which is what reacted. And needless to say, you will get 0.25 grams. All right. Now, I must admit, guys, this was not really one of those easy questions, right? I would appeal to you to watch this over and over just to understand, right? So we found out what was the number of moles of calcium carbonate that actually reacted. We subtracted it from the initial mass, right, that was given, and that gave us the mass of the impurities. Okay, right, and that is how the cookie crumbles in terms of acids and bases. That would have earned you 9 marks. 9 marks that were worth it, guys. I am way over time, 15 minutes over time, and I'm sorry that I couldn't take the questions for those of you that were on YouTube. I'm not sure if there are any people that are joining us on TikTok, but guys, this is where we are going to leave our live, okay? And for my students, are you guys okay so far? I hope that this session was well worth it, right, guys? All right. I know that we've taken longer than we should have, all right? But nonetheless, I hope that it will assist you. Guys, tomorrow it's Father's Day, so please do say, please, if you've got a father or a father figure, do wish them a happy Father's Day and do something special as well. And we are commemorating Youth Day, so do the right thing, okay, guys? But from me for now, it's really been a pleasure. For those of you that are joining us live on YouTube and on our social media platforms, it's really been a pleasure. If you do want to join these guys that are in our class, you can get or reach out to us. The email address is info@mlungisinkosi.co.za. All right. You can also get in touch via our WhatsApp number. That's 064 554 7199. I'll say that again. That's 064 554 7199. That's the number that you can reach us on, and we will try to respond as promptly as possible. Well, from me for now, it's really been a pleasure to be with all of you, and I will see you guys again next time. Guys, have yourself an awesome one, and please do best when it comes to chemistry on Monday. Okay, on Tuesday. Well, I know it's a long weekend. Sharp, sharp for me.
Thank you, sir.
All right, you are most welcome. Thank you, guys.